A lightning storm is a magnificent sight, so powerful, so beautiful, so electric. In this chapter, we will be discussing energy that is derived by electron transfer, just as this lightning bolt is doing that. We will discuss batteries, hybrids, and solar panels. A battery is a system for the direct conversion of chemical energy to electrical energy. Batteries are found everywhere in today's society because they are so convenient, transportable, because they are convenient, transportable sources of stored energy. The batteries shown here are more correctly known as galvanic cells. A galvanic cell is a type of electrochemical cell that converts the energy released in a spontaneous chemical reaction into electrical energy. If you didn't get that definition, it's also on page 332 in your text. Several of these combined is a true battery, like the one we have in the car. A galvanic cell is a device that converts the energy released in a spontaneous chemical reaction into electrical energy. This is accomplished by a transfer of electrons from one substance to another. The nickel and cadmium battery that you see here, the electrons are transferred from the cadmium, which is right here, the light blue, to the nickel, which is the red sheets, in this picture. By placing the compounds in sheets, the surface area is increased and therefore able to react more readily because there's even more contact. The electron transfer process involves two changes. The cadmium is oxidized, which means the elements are losing an electron, and the nickel is reduced, which means the element is gaining electrons. Notice that the electrons are on the left for the nickel. That means it's gaining it, and it's on the right for the cadmium. That means it's losing it. Half reactions allow us to track the electrons. These are half reactions right here when it just talks about one element at a time. In this example, cadmium is losing 2 electrons, which is why the 2e minus here is placed on the right hand side. Nickel is gaining 2 electrons, which is why the 2e minus is placed on the left hand side. Overall, the electrons need to cancel out because they can't have any extra ones floating around. There are several different mnemonic devices to remember which is which. For this particular textbook, they use the terms oil, O-I-L, and rig, R-I-G. Oil is oxidation is loss of electrons, so O, loss. Whereas rig is the reduction is gain of electrons, so R, gain. So that's why they come up with oil rig. The transfer of electrons through an external circuit produces electricity. The flow of electrons from one region to another that is driven by the difference in the potential energy. To enable this transfer, electrodes, which are electrical conductors, pieces of metal, are placed in the cell as sites for chemical reactions. These are two different electrodes. There are two different electrodes, a cathode and an anode. Reduction occurs at the cathode. The cathodes are receiving the electrons. Oxidation occurs at the anode. This is the source of the electrons. The difference in electrochemical potential between the two electrodes is the voltage, which is in volts. So the amount that one wants to lose it and one wants to gain it is that potential. The difference between electrical potentials will provide the voltage of a battery. It is essentially how badly one compound wants to give up electrons and how badly the other one wants to take them. The greater they want to do this, the higher the voltage will be. Most people are familiar with simple alkaline cell batteries. Each of these provide 1.5 volts, but the bigger the bigger the battery, the longer it lasts. Alkaline batteries consist of mainly zinc and manganese. Mn is manganese. It is referred to alkaline as a result of the reacting in a basic solution. So it's alkaline because it's basic. Unlike car batteries, which are in an acidic solution. The picture you see here is how an alkaline battery is formed. The center rod here, which is that bump you see on the battery itself, is the cathode. Remember, this is what is receiving the electrons. The manganese is absorbing 2 electrons in the process. Zinc is the anode, which is where the electrons are being derived from. So the electrons are passing from the zinc to the flashlight, and then coming back down to the manganese via the graphite rod. This chart provides some examples of batteries and the charges that they give off. Alkaline is at the top with 1.5 volts. Each alkaline battery will have the same voltage. It's the size of the battery that alters what the public sees as, quote, volts on a package. So a 9-volt battery has the equivalent of 6 alkaline batteries inside of it. Notice that scientists and engineers have used larger potential differences for batteries to power items that need more energy, like the lithium and laptops. It is over twice the amount of the alkaline. If something needs a lot of energy, manufacturers will make what's called battery packs. That are several batteries linked together. Earlier, I contrasted alkaline batteries with car batteries. Car batteries consist of 6 electrochemical cells. So notice these. Each providing 2 volts of electricity for a total of 12 volts. The cathode and anode plates have lead between them. The anode plates are solid lead, which is fairly flimsy. The cathode plates are lead dioxide in them. The solid lead gives off 2 electrons as it combines with the sulfuric acid to make lead sulfate. The electrons are then passed through the engine and returned to the battery as lead dioxide. This is what is happening while the battery is being discharged. Luckily, we have alternators that reverse the charge of the battery to back it up. Hybrids combine gasoline and batteries. This is mentioned on page 341 in your text. The electric motor draws power from the batteries to start the car moving and to power it at low speeds. The car becomes charged during deceleration and braking. The gasoline engine assists the power during normal driving with the assistance of the battery when extra acceleration is needed. By using hybrids, you can reduce the carbon dioxide production by 18 tons in a lifetime of a car. The plug-in hybrid vehicle is another example of a hybrid car. It uses rechargeable batteries for short daily commutes to run an electric motor and then switches to a combustion engine for longer travels. Although these are rather expensive now, they are becoming more popular, and the supply and demand will increase over time, most likely driving down the cost. Other automotive advances include cars powered by fuel cells. Chemical energy is a fuel directly into electricity without burning the fuel. A fuel cell is a galvanic cell that produces electricity by converting the chemical energy of a fuel directly into electricity without burning the fuel. Both fuel and oxidizer must constantly flow into the cell to continue the chemical reaction. The hydrogen stored in a tank enters the proton exchange membrane and combines with oxygen to produce water. The hydrogen gas gives off 2 electrons, while the oxygen gas takes in 2 electrons. This exchange creates nearly 10 times the amount of energy as gasoline. It is also way more efficient. This is a direct comparison of fuel cells to combustion engines. You will notice that not only does the fuel cells create more energy, it also reduces noise, carbon dioxide, and other unwanted byproducts. It may be a problem to refill your hydrogen tank if you decide to go this route with your next car. Just like the current gasoline-powered cars, the fuel cell car can drive around 300 miles before refueling. Unlike the gasoline car, there are only around 70 hydrogen refueling stations in all of US and Canada. Engineers and scientists are trying to find better alternatives for storing the gas on the car as well. Right now, it is rather cumbersome and hard to deal with, but innovations are occurring. If the hydrogen economy becomes reality, where will we get the hydrogen gas? Another issue is the cost and production of the hydrogen gas. Hydrogen is extremely reactive and does not keep for long periods of time. One potential source is fossil fuels. But these reactions produce carbon dioxide and carbon monoxide. Electrolysis of water could also be used, which is when you put an electrical charge through water to separate it out into its elements. Unfortunately, it takes a lot of energy to produce this. New methods are being developed using waste in landfills and sunlight to heat up carbon dioxide and methane to produce hydrogen gas, as you can see with the second reaction. The carbon dioxide and the methane are trying to produce hydrogen gas. As mentioned in the previous slide, water can be broken down into hydrogen and oxygen gases through electrolysis. When this occurs, the amount of hydrogen gas is twice that of oxygen. But producing the electricity to split up the molecules could become problematic. Electrolysis is essentially taking water and putting electricity through it to make it separate. Scientists are working on a way to use the sun's energy rather than fossil fuels to break down the water molecules. Unfortunately, these are only less than 10% efficient. But scientists and engineers are continuing to work and improve this process. While we're on the topic of sun's energy, let's jump to photovoltaic cells. Is this the energy of the future? The sun provides an awesome source of energy. Our society has been using photovoltaic cells or solar cells at a minimum level, but we will all begin picking up the natural form of energy as a way to conserve our natural coal and petroleum supply. This graph indicates the areas of the country that are most likely to be successful with the energy of the sun. Notice that the areas in the southwest receives the most sunlight. They would have the most luck with the solar energy. Photovoltaic cells is one method to harness the sun's energy. These are devices that convert light energy directly into electric energy. They're sometimes called solar cells. If you did not catch that, that is on page 354 in your textbook. In this picture, the top picture is of a single cell. It only takes a few of these to power a calculator. Several of these are linked together to make a module. A module would be enough to power a traffic sign. Finally, an array of several modules linked together. These are used to make solar panels. Depending on the size of the house, one may need a dozen or so solar panels to power a house. You would need 100 of solar panels or arrays linked together to have any type of large-scale industrial power. Voltaic cells are made of semiconductors. These are materials that have a limited capacity of conducting electric current. This is on page 355. This means that the electrons can move around, but not nearly as much as they can with metal. If an electron absorbs enough energy from the sun, it gets a chance to free itself and move around. This movement is how electricity is conducted. There are two types of semiconductors, N-type and P-type. The N-type semiconductor has an extra electron that is free to move around. This is giving it an edge because it does not have to wait to absorb the energy to move. A P-type semiconductor has fewer electrons. There's a hole in here. This gives a spot for electrons to move in and out of. This then provides locations for electrons to move around. It also makes it easier to conduct electricity. Both of these can be created by what's called doping the silicon with other elements. Doping is a process of intentionally adding small amounts of other elements to pure silicon. The N-type would be doped by arsenic, which has more electrons. The P-type would be doped with something like gallium, which has fewer electrons, hence making the hole. The two layers of semiconducting materials are placed in direct contact to induce a voltage in the PV cell. So they're placed side by side so that way they can move around even more. The typical photovoltaic cell has both P and N-type semiconductors. Currently, photovoltaic cells are only about 15% efficient. A coal power plant is 35 to 50% efficient. Some researchers are trying to increase efficiency by placing several P and N-type semiconductors right next to each other. They believe that this will increase the efficiency of the process. Even at low efficiencies, it is still considered cost-effective since the sun's energy is free. This also gives you a comparison. If this is the width of a human hair at 50 micrometers, one layer of this is only 15. So that's about a third of the width of a human hair. A newer version of the photovoltaic cells are made of cadmium telluride. These are far thinner and more flexible than the ones made of silicone. They can even be placed inside roof shingles and be far less intrusive looking than the former ones. Photovoltaic cells can power water pumps in remote areas of the world where there is no access to electricity, like you see here. Spain leads the world in the amount of electricity powered by solar panels. Next is Germany. The picture you see on the left is a solar park in Germany. It produces 12 megawatts of power. It is thought that we would need 7,200 square miles of solar panels to power the U.S. This is approximately the size of New Jersey. It's time to make important decisions and advances in alternative energy technology and new sources of renewable energy. No single energy source can meet our global needs, but we do need to start moving towards renewable resources to produce minimal waste products. Solar thermal energy is a process where the heat given off by the sun is intensified by angling the concentration of the sunlight. Windmills work kind of the exact opposite of fans. Fans take electricity and produce wind. Windmills take the wind to turn turbines to produce electricity. Hydroelectric plants is another form, produce electricity by the movement of water. As water moves, whether it's a waterfall, dams, or tides, it turns a turbine, which then produces electricity. Finally, geothermal energy uses the Earth's heat to produce usable energy, whether it is heating a home or driving generators. We as a society need to think about different ways to produce electricity so that we are in a win-win situation, unlike where we are now.